Okay. Good afternoon, everybody. I ate a whole foot-long sandwich. Daniel, if I fall asleep, will you wake me up?
Sure.
Okay. Oh. Well, somebody else wake me up. All right. I prepare a lot of lectures, and in fact, I often prepare in advance my lectures. In fact, sometimes weeks and weeks and even months in advance. And I almost always find that just as I'm about to give the lecture, I change my mind. That's not the lecture I want to give. And I especially do that the second lecture after the first lecture. Realize that what I really wanted to talk about, the first lecture was fine, but to build on the first lecture, the subject that I really wanted to talk about is a little different than the one that I prepared, and that happened again now. I kind of realized that the subject that I wanted to talk about here was a particular aspect of complexity, and in fact, you could call it the statistical mechanics and thermodynamics of complexity. But certainly also how that statistical mechanics and thermodynamics plays with gravity, for sure. We already know that thermodynamics plays very heavily with gravity. In fact, some of the gravitational laws, things that we ordinarily think of as laws, Einstein's equations and so forth, must somehow be statistical laws. For example, the fact, which follows from Einstein's equations, that horizons grow and never shrink, that seems to be a dynamical law, is really, when it comes down to it, the second law of ordinary thermodynamics, that entropy always increases. That's a statistical law. It is true except when it's not true. When it's not true, it's very highly fine-tuned situations and so forth, where you might be able to make entropy decrease. And so at least some of the laws of general relativity, my own guess is all of them, are in a sense statistical. But in order to see that, I think we have to extend our concepts from ordinary thermodynamics, which has to do with entropy, to a new kind of thermodynamics that has to do with complexity. And so that's what I'm going to talk about today. Show you how it interplays with black holes and so forth. But let me just review extremely quickly what I said last time with one basically simple sentence. That the complexity of a quantum circuit is a kind of entropy of an auxiliary system, not the real system that you were talking about, but a system which really represents the evolution of the wave function, or if you like, the evolution of unitary time development operator. In other words, a point moving on SU2 to the k, a point moving, that is the evolution of the wave function, in this case the evolution of the wave function of a maximally entangled state with time, and it's a point moving in a space, and you can think of it as a dynamical evolution of something. The entropy of that auxiliary system is complexity. It's not the real entropy, it's not the ordinary entropy of the quantum system. That's the main takeaway from last time, that complexity is the entropy of an auxiliary system. Any questions about that? None, all right. I don't have a complete theory of black holes which expresses it as a collection of qubits. The closest thing we have is something like SYK, but in general, I certainly don't have a theory which says this black hole can be represented by qubits in this or that way. The techniques that I'm going to use to argue that things like complexity are very important in black hole physics is a kind of technique of comparing things that we know about gravity to comparing them with things that we know about quantum circuits, and showing similarities, showing how the similarities work. And that will have to replace, for the moment, a kind of bottom up is, I never know, is it bottom up or top down? I'm not sure which, but a derivation of the ideas from some first principles. We'll work with two kinds of systems, gravitational systems and quantum circuit kind of systems, and I'll show you how they parallel each other. All right, and they parallel each other rather interesting ways. And that's what this lecture will be about, but particularly focus on thermodynamic and statistical issues. The thing I'm going to downplay is the connection between, I'll speak about it a little bit, but downplay the connection between action and complexity. That's sort of a separate subject. I will talk about it just briefly. Okay. Let me write the sort of chart here of some of the similarities. On the left-hand side, can everybody see? Yeah. On the left-hand side, I'll put some things about circuits, quantum circuits. I don't know why they're called quantum circuits. There's nothing circular about them. Circuits and black holes. All right, first of all, in thinking about circuits, we'll introduce a number of qubits, k. I'll just write k here for the number of qubits in the circuit. And since what we're going to be thinking about is problems in which the circuit evolves fairly random states, we can also say in general the number of qubits will be comparable to the ordinary entropy of the system. You can think of it as the entropy of the quantum computer, ordinary entropy, and that's proportional to k, number of degrees of freedom. And on the right-hand side, well, okay, we have a circuit. Here we have black holes with entropy S, and I'm going to identify, at least qualitatively, the entropy of the black hole with the number of qubits in the circuit. Let me say what that means, first of all. What it means is that you're going to try to represent the black hole, or whatever system you're talking about, with a minimal number of qubits. I can have a system described, n equals 4 super Yang-Mills theory, the whole thing. Possibly you might be able to describe it in terms of qubits. How many qubits? A huge number of them, because ADS is very, very big. But now I put some small object into ADS, a small black hole, a relatively small black hole. How many qubits do I really need to describe that small black hole? Surely I don't need all the qubits that might represent things out near the boundary, so I should be able to express it in terms of a smaller number of degrees of freedom than the actual full system has. For example, if I wanted to study you over there, would I need all the degrees of freedom in the entire universe? No, probably not. I could build a shell around you of, let's say, 6 feet in diameter and get a pretty good description of you with just the degrees of freedom within that shell. Also, you too. All right. Okay, so you don't need all the degrees of freedom. How many degrees of freedom do you need to describe a system of entropy S? Well, if you cut the number of degrees of freedom down to less than S, you simply can't describe the entropy of the system. So I would say, in general, the minimal number of degrees of freedom that you can get away with is possibly comparable to the entropy of the system, and that's what I'm doing here. I'm saying black holes of entropy S can be represented in terms of a system of qubits where the number of qubits and the entropy of the black hole are more or less comparable. So we're going to assume something like that. We do this all the time, but rarely state it. Okay, so that's one correspondence. Number two, in circuit theory, I defined for you last time a sort of standard architecture. The standard architecture of a circle is, first of all, k local, this little k here, and for the most part, I will deal with 2 local. 2 local means the circuit is built up out of gates, which are 2 qubit gates, and all to all. All. In black holes, very similar things are going to be true. We're going to describe the black hole by a system of degrees of freedom which are also k-local, maybe not 2 local, possibly a little bit different, but again k-local, but now they won't be k-local gates, they will be k-local Hamiltonians. That means the Hamiltonian is built up out of collections of terms, each of which involves no more than k degrees of freedom. And second of all to all. Now, why all to all? What is it about black holes that tells us that they should be all to all? And the answer is the fast scrambling properties of black holes. I hope somebody has talked about that a little bit. I mean, I'm sure that Douglas did, but he might not have said that that's what it was. The fast scrambling properties are the rapidity which with black holes thermalize. And the only way to get them to thermalize that fast is for every degree of freedom to potentially be able to interact with every other degree of freedom. And that's this all-to-all property. So again, another parallel. Now here's a very important parallel that I'll emphasize as we go along. For circuits, you need a clock. Remember, the architecture of the circuits is, I won't draw the circuit here, but I defined it in terms of dividing up time into intervals, and in each interval, every qubit gets to interact once. You need a clock, or you need a timekeeper. The timekeeper, or the time, which measures the number of intervals, the number of basic intervals, I'll call tau, and we can call that computer clock time. On the right-hand side, the analogous thing is not the Schwarzschild time of the black hole. It is the Rindler time. And we're going to show you why that is as we go along. Computer time is Rindler time of the black hole. I assume you know what Rindler time means. What's that? No, up to a factor of 2 pi over beta. Rindler time is dimensionless. Right. Let me write Rindler time, yeah, okay, let me write Rindler time, and I'll also call it tau. Rindler tau, and it's equal to Schwarzschild time, conventional Schwarzschild time, could also be the boundary time of a holographic theory, 2 pi over beta, where beta is the inverse temperature. That's the Rindler time, and this is a universal, this is very universal. If you don't know this, it's a good thing to go as a little exercise and go and convince yourself that for any black hole, the connection between the Rindler time and the asymptotic time is 2 pi over beta. It's a little exercise that I once did long ago. And finally, on this side here, there's a particularly, if I'm interested in the kind of quantum, well, okay, the kind of quantum circuits that could describe maximally entangled qubit systems, what I want to write on this side here is the thermofield double state. The thermofield double state, that's a system of 2 black holes, so it basically doubles the number of degrees of freedom. On the left-hand side here, you should identify that with a pair of quantum computers which are entangled with each other, and they're entangled with each other in the simplest of all possible ways, namely a product of Bell pairs. One writes that as 0, 0 plus 1, 1 divided by square root of 2, but I won't put the square root of the 2 in, and then people like to write that with a. This means a product of Bell pairs, k of them, k Bell pairs, and that replaces the thermofield double in the analogy between, or in the correspondence between circuits and black holes. Okay. I like to stop from time to time and ask people if there are any questions. So,
Sorry, what is this k?
What is what?
The Bell pair product.
That just means k, the same k. Instead of 1 Bell pair, we have k Bell pairs, so that means k qubits on one side, k qubits on the other side, enough to describe 2 black holes, but entangled, okay? And that's the thermofield double state, or the analog for it. Now, let me come now to black holes and pose for you a very fundamental paradox. This should have been one of the very, very fundamental paradoxes about black holes if anybody had thought to think about it. In fact, I did. This paradox has confused me since around 1981. So let me tell you what the paradox is. If you followed anything I've been doing for the last few years, you probably know what it is, but nevertheless, I'm not trying to surprise you, I'm just trying to inform you. Let's take an eternal black hole. There are its horizons. Okay. And now I want to foliate it. I want to foliate it by space-like surfaces of a particular kind. Let's start at t equals 0. And I'll draw dotted lines. Dotted lines I will always use for the exterior regions of a surface. To draw these surfaces properly, I'm going to draw an asymptotically late surface over here. And the rule is you pick a point on the left, a point at the right, at the same time. T left, T right. And bridge them with a space-like surface that has a particular property, particular geometric property. What I want is to define the surfaces in a geometric way which is not coordinate invariant, an invariant way. And one nice way to make invariants is to minimize or maximize something. And in this case, what I will do is maximize the volume, the spatial volume of the surface. Outside, I'll draw it dotted. Inside, I'll draw it solid. This is very hard to draw accurately. So I won't draw it accurately. When you get way up here, there's an asymptotic such surface which goes through the points at infinity. And what happens when you get up very late is the corresponding surface for the late time stays very close to the asymptotic surface until at the last minute it departs and goes, oops, this should be dotted, like that. And as you go up in time, they get closer and closer to this final surface, but always they jump out at the last second and jump out to the point at which they're anchored, the anchoring points. All right, now, I can also draw the same kind of foliation into the past. I won't try to draw it as accurately. Not that I was accurate before, but there it is. And it's a complete reflection of the picture on the top. Okay. Question. Well, first observation. Observation is that these surfaces are growing in the interior. They're growing, they're getting bigger and bigger, their volume is growing. And in fact, their volume is growing without bound, at least classically. Just keep growing forever and ever. Likewise into the past. First of all, it reminds me about horizons, the fact that horizons grow. But that we understand. That has to do with the thermodynamics of entropy, the growth of entropy and the second law of thermodynamics. Here something else is growing, and it's most certainly not entropy, not ordinary entropy of the black holes, because these black holes on each side here are in perfect thermal equilibrium in the thermal field double state, and their entropy is absolutely constant. The entanglement entropy between the two sides is constant. No entropy is growing. So the puzzle is what is growing here? What is the quantity which is growing if not entropy? Now, this reminded me of something. This goes back a long ways. I was puzzled by it. It reminded me of what you could call an entropy bounce. I'll call it an entropy bounce. I'll tell you what it is. It's a crazy thing. It doesn't really happen in nature, not easily. Imagine that we have a box. This is not a Penrose diagram now, it's a box. And it's got gas in it, 10 to the 30th molecules or whatever. And you start them out on purpose, all sitting right on top of one another at rest. The entropy of that is very low. It has no thermal entropy because they're all at rest. And it has no positional entropy because they're all at the center. And so it's a very low entropy state. Now we can imagine that the molecules are repelling each other, and we let it go. We let it go, what happens? They spread out, they fill the box, they come to thermal equilibrium. Okay? What would happen if instead of running it forward, we ran it backward in time? Run it with the Hamiltonian, but run it backward. Well, exactly the same thing would happen. It would grow, fill up the box, and come to thermal equilibrium. That whole trajectory from remote past to remote future involves the molecules initially in thermal equilibrium, suddenly deciding to all swoosh toward the center of the box, coming to the center of the box, and then exploding outward and coming back to thermal equilibrium. This is a solution of this is a solution of the Newton equations of motion, even if you're not likely to see it in the real world. One might ask, why are you unlikely to see it in the real world? Well, first of all, let's plot the entropy as a function of time. The entropy as a function of time bounces, that's why I call it an entropy bounce, and then comes to thermal equilibrium. Now, if you waited long enough, an exponentially long amount of time, you would see this kind of thing happening over and over, but that takes an exponentially long amount of time. Classically, incidentally, I'm talking now about classical molecules. And these would be called Poincare recurrences, and the Poincare recurrences themselves would look like the entropy bounce. So in fact, it can happen in nature, just very rarely. Okay. From here to here, or from here to here, is an entropy bounce. That kind of looks like what's happening here. Something in the past, decreasing, coming to some minimal value, and the thing which I'm thinking about now is the volume of these surfaces inside the horizons. Forget the part outside the horizons, let's concentrate on the part inside the horizons. It's bouncing, it's going through some sort of bounce. Now, as I said, the dynamics of horizons and the fact that horizons expand, that's entropy. Okay? What is it here? What is the quantity which is doing this? My mind, that should have been a major puzzle about black holes for all these years. It's just nobody thought of it. I don't know, maybe one thought about it. I thought about it a long time ago, but forgot about it. So there we are. Is this an artifact of the two-sided black hole, or does something like it even happen for a one-sided black hole? And the answer is yes. The answer is no, it's not an artifact. Yes, it happens for one-sided black holes. So let's just draw a one-sided black hole, an ADS one-sided black hole. Singularity up here, horizon over here. This is r equals infinity, the boundary. This is r equals 0 over here. You might throw in some matter. The matter would come in here, create a horizon. Incidentally, it's the growth of this horizon which is governed by the second law of thermodynamics, of ordinary thermodynamics. And now we can do the same kind of game. Anchor points at the edge, and draw maximal surfaces. Down here, they would just look like this. Some last maximal surface would stay completely outside the black hole. And then the next one would sort of be outside and then go in. Again, same pattern, some asymptotic surface up here, and the same kind of deal. Something is growing. That something is defined geometrically. It's invariant under coordinate transformations. It should have a description as something in the boundary field theory, in the boundary theory of a holographic theory. What is that something? So that's the question we want. Now, I'm sure you can all guess. If I would ask you, what's the answer? Nobody? Complexity, of course. Right. Right, so I'm not trying to surprise you, as I said. Just trying to show you what's at stake. Let's talk about the evolution of the growth purely from the general theory of relativity point of view. Just how does general relativity tell you that these surfaces grow? Let's see if I can do this. Good. Good. Huh. Yeah.
How long do
I couldn't hear.
How long do you expect the picture hold?
How long do I expect?
This picture is
Oh. Yes, that's a very, very good question. Classically, forever. Classically, forever, and we will come to how long you expect it to hold quantum mechanically, not forever. Okay. All right, the formula for the growth of the volume of the Einstein-Rosen bridge, or whatever we want to call it, the wormhole, or just that surface in there, the part inside the black hole, GR gives an answer, and it's the volume by dt. This can be ordinary T now, not Rindler time, is equal to the area. This equality here is up to some factors of order 1, which I don't remember offhand. The area of the horizon, the temperature, I'm thinking classically now, so temperature means surface gravity.
So if you just have a dynamical QFT, say, or any quantum mechanics, this complexity is growing, right? No matter there is a black hole or not.
Yes, but very slowly.
How does this picture distinguish itself from the usual?
Yeah, if you have very dilute degrees of freedom, let's just say a pair of qubits, okay? A pair of qubits, and let's say they're entangled. You start them out, and you ask, does the complexity increase? No, it can't increase very much because the maximal complexity of a qubit is 1. So it doesn't increase very much. Now, if I have a whole bunch of qubits which are separated from each other and not in close contact with each other, basically it's the same thing. The complexity can't increase because the maximal complexity of a single qubit is 1, and they're all independent of each other. Now you make them interact, yes, the complexity will start to grow, but very, very much slower than in a black hole. Very, very much slower. So the answer is yes. Now, if you believe in this principle called ER equals EPR, then any entangled system has a characteristic wormhole kind of geometry associated with it. And so, yes, even in ordinary systems which are developing complexity, let's say they're entangled, you can say, I'm not sure it means very much, but you can say that the Einstein-Rosen bridge connecting them grows with time. But I think the natural place for these ideas is in black hole physics. Okay, let me decide, where are we? Here we have a formula. No, it's not finished. The temperature goes here, which classically just means the surface gravity. And in an ADS context, there would be an LADS here. You can check the dimensions of this, and hopefully it makes sense. I think it does. And this is the pure general relativity rate at which the volume of these interior surfaces grow. I'm not going to derive that. It's not hard to derive, but I'll leave it to you. Okay, now let me define little c here. Again, I don't want to surprise you, but later this little c is going to become complexity. But for the time being, it's a pure gravity concept. The volume divided by G LADS. And rewrite this equation for C. Equals area divided by G times T. Area divided by G is entropy, S times T. Whatever this quantity is, and it's got some quantum mechanics in it because it has G in the denominator, which means it has some H bar in it, but it just grows as the entropy times the time. Okay. Let me now use my correspondence up there and write this in terms of Rindler time. Rindler time, again, is tau is equal to 2 pi T over beta, but let me just put temperature here in the numerator. If I rewrite this, what I'll find is that the C by the Rindler time is just equal to the entropy. What I want to compare this now is with a quantum circuit. The quantum circuit, remember how the quantum circuit works. Here's the quantum circuit. We divide it up into time intervals. This is delta tau equals 1. For the moment, there are two different taus. One is the computer clock. The other is the Rindler time of the black hole. And then in each one of these intervals here, k/2 gates occur. That means unless there's shortcuts, unless there are collisions in the sense in which I said last time, which are rare, unless there are collisions, it means that the complexity will be growing as the number of gates in here. And so we can say, in this case here, for the circuit, d complexity will have a little curlicue on it here, times d tau is equal to the number of qubits, in this case the number of qubits divided by 2, or is equal to k. k/2 or k, I'm not going to distinguish those two. And now we go back to the top, and we see that k is to be identified with the entropy of the circuit. Let's call it the end, let's just call it S now. So we see a parallel here that the rate of change of the interior volume there has the same behavior as the rate of change of complexity for the quantum circuit. If I identify Rindler time with circuit time. That's one of the bases for, well, let's leave it here. That's one of the bases for this connection between the two different kinds of times. In which one? No. I got rid of the, it went down here someplace. Let's see, where did it go? Yeah, okay. Right. I purposefully scaled it out. Okay. That suggests that we identify complexity with exactly this quantity, the volume of the Einstein-Rosen bridge divided by g Newton divided by LADS. That would be the correspondence that this thing calls for here. Now, somebody asked, how long do I expect that the classical gravity equation makes sense? And we could ask correspondingly, how long do we expect that the growth of complexity makes sense? Are they similar? Classically, the growth of the Einstein-Rosen bridge takes place forever. But let me right now make an argument that quantum mechanically that cannot possibly be true. I'm going to make the argument, it doesn't have to be made this way, but I'll just, I would like a diagnostic that measures the length of a wormhole. There's the wormhole connecting the two boundaries. And supposing at some time the length of the wormhole I'll call capital L. It is whatever. The length of the wormhole is capital L. And let me take some quantum field out here and some quantum field out here and ask what the correlation between them is. I maintain that the correlation between them, due to the fact that they're connected via the wormhole, is basically e to the minus the wormhole length. Like all correlations, they tend to decay exponentially. I'm actually talking about massless fields, but a massless field trapped in a wormhole behaves like a massless field in a waveguide. It behaves with a mass. What mass would it behave with? Turns out the right mass to put in there is 1 over LADS. And you can study these correlation functions, and you'll find out that phi left, phi right can be expected to go like exponential of minus L of t, where L of t is the momentary length of the wormhole. This is what you would expect. I'm only doing this in order to connect the length of the wormhole with something that you could think of as more or less experimental. Now, this will not go on forever for a variety of reasons. First of all, when this gets too small, it gets dominated by noise. But there are ways to filter out the noise. But for sure, you cannot expect this to go on for longer than a doubly exponential time. Doubly exponential in the number of qubits, or the number, or the entropy, exp, s. It can't go on longer than that for the simple reason that there's a Poincare recurrence theorem about quantum mechanics. The state of the system will eventually recur. So if we started with a small black hole, with a small wormhole to begin with at the thermal field double point, and you wait long enough, it will get small again. The meaning of that, among other things, is that the correlation function will grow and become maximum again after a sufficiently long time. We can interpret that as the wormhole length also undergoing Poincare recurrences. So for sure, you can't expect it to go on for more than a doubly exponential amount of time. This is just a basic principle about quantum mechanics. If you wait long enough, the state will return to what it was. I would maintain that it will break down long before this doubly exponential time at a singly exponential time. And the argument goes something like this. Supposing we watch this wormhole growing, and we think of the length of it as some kind of operator, some kind of geometric operator. L is something in the bulk Hilbert space, let's say. As the system grows, it runs through states. It runs from one state to the next state to the next state. Yeah.
Do you need a black hole to write C equals V over G analogies?
Well, no, you don't need a black hole, but there's no black hole. V is 0 and C is 0. And C is 0.
If I have a toy black hole like an entanglement wedge,
Like a what?
like an ID surface,
Let's say a Rindler horizon. Yeah, okay. Then this formula does apply, but the only thing you have to keep track of is that the area is infinite and the volume is infinite, so you have to think about it as volume per unit length along the Ryu-Takanaki surface.
okay.
Yeah, so,
I have a follow-up question.
yeah.
In that case, I can make another proposal that relates the volume to a different quantity, information theoretic quantity in the CFT. I can take the volume and foliate with Ryu-Takanaki surfaces that go to different depths in the boundary. And in the boundary, I can integrate on the entanglement entropy on different interval.
Different depth, you mean different depth into the wormhole?
Yeah.
Yeah, well, okay, this is
Is this not satisfactory, or what's wrong with it?
it depends on which entanglement you're looking at, what I call vertical and horizontal entanglement. Are you talking about entanglement between the left side and the right side?
Yeah.
That's constant, doesn't change.
But I'm changing the length of the. So I fix one horizon, the Rindler horizon. I call it.
If you're interested in left-right entanglement, then the right surface, If you're interested in entanglement between the left side and the right side, then the right entangling surface is just this. And that doesn't grow with time. If you're interested in what I call the vertical entanglement, where you divide the wormhole in half and look at the upper half entangled with the lower half, this is the Maldacena-Hartman calculation. That entanglement increases but saturates after about a scrambling time and doesn't continue to increase.
Sorry, I think I wasn't clear. I don't want to be in the eternal black hole geometry. I just want to take one pure ADS, one global ADS spacetime, and I want to take a ADS 3. Let us be.
Okay?
Let's take the simplest case, and
Okay.
I want to fix L max in the CFT
L max.
or theta max, some circle with maximum, some arc of a circle with maximum angle. And I have a short distance cutoff in the CFT, and and I want to keep foliating the.
I think we're best off doing this in the discussion, because I'm not following you, and so let's come back to it. All right. Okay, so good. So the classical has to break down. Now, quantum mechanically, as the wormhole gets bigger, let's assume that different length, macroscopically different length wormholes correspond to orthogonal states. That seems reasonable. And as the wormhole grows, you therefore run through a sequence of mutually orthogonal states. Well, how many mutually orthogonal states are there in the Hilbert space of k qubits? The answer is e to the k, or e to the s. That's the number of states that you run through before you've got to recycle and possibly become a superposition of all the previous states. When that happens, clearly the expectation value of L cannot increase beyond that. And that will happen at a time of order e to the s. So it seems reasonable to me that the classical description has to break down by time e to the s. Other people have different arguments for the same thing. And what we know about the quantum circuit is it reaches maximal complexity also at time e to the s.
You're distinguishing between e to the s and e to the 2s?
Oh, there isn't a distinction between e to the s and e to the 2s. Am I going to draw that distinction? Not now. It's 4 to the s to be a little more precise. Right. Good. Yeah. Curvature of what? Extrinsic, intrinsic curvature on the slice? You mean on each one of these slices? The extrinsic curvature is 0. If we were talking about, let's say, BTZ, 2 plus 1 dimensions, the intrinsic curvature would be 0 because they would be cylinders. Yeah. Cylinders of constant. On the other hand, if we were higher dimensions, the circle would be replaced by a sphere of some sort, so there would be. But the extrinsic curvature of the slices is 0. That's because they're stationary volume. Okay. Yes?
Where does the multiplicative ambiguity in complexity?
There is a multiplicative ambiguity, but there's no multiplicative ambiguity in what the maximal entropy is. Oh, no, sorry. In when the maximal entropy is reached. Yeah.
I mean, where does it show up in this expression?
Oh, okay. So up to some unknown numerical factor, and the factor which will in general depend on your specific definition of complexity. I suppose one can make the conjecture that there's some very specialized notion of complexity which would fix that constant, but I'm nowhere near understanding that, so we can't go there. Okay, good. So we have a kind of match. The growth rate is comparable when expressed in terms of Rindler time or computer time. The breakdown of the classical description occurs at the same time as the breakdown of the growth of complexity. And so we make that conjecture. It is a conjecture that the complexity of the quantum state, well, I've written it over there, but I'll write it again. The complexity of the quantum state is to be identified up to a numerical constant with the volume of the wormhole times G L ADS. Now, people who like tensor networks like to imagine that the wormhole is filled with a tensor network bridging the two sides and describing the quantum state on the boundary, and think of the complexity as the number of nodes, for example, in the tensor network. It's the same idea, or a very similar idea. The wormhole grows, the tensor network has to grow in order to accommodate time evolution, and the number of vertices in the tensor network will grow the same way. Okay. My conclusion is that for the past 30 years that I've been confused about this problem, I was confused because I never heard of complexity. And I was trying always to build in this growth of the interior into the second law of thermodynamics and always failing. Let me come back to the single-sided wormhole here for a moment. In the case of the single-sided wormhole, it is not in thermal equilibrium for all time. And in fact, when the matter comes in and creates the black hole, the entropy does increase for a while. But how long? Well, for a very short time, a scrambling time. That's about a millisecond for a solar mass black hole. Whereas, at least classically, the growth of the interior there takes place forever, or according to this, for an exponential time. So none of this is an artifact of the two-sided black hole. Incidentally, the one-sided thing here, Ying Zhao and I called the bridge to nowhere. Have you ever seen pictures of bridges to nowhere? They start out and they just stop. Same here. Was it Sarah Palin who had one of those built, I think? And she stopped it. Okay. 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 All right, now we're going to come. Good. No, sorry. The message that I want to deliver now is that that the interior of the black hole, its growth is not the second law of thermodynamics, it's the second law of complexity. Complexity tends to increase. Also a statistical law. Okay, now I want to talk about the complexity of precursor operators. Let's see, let's get rid of this over here. The complexity of precursor operators. The point is to try to find more examples where there's match. Yeah?
If then the black hole starts evaporating,
What's that?
the black hole starts evaporating, losing its mass due to high radiation.
Well, these are ADS black holes. They're in a box. They can't radiate. Yeah.
There is no dynamical black hole, which, like, you are in one.
The black hole is very dynamical.
Then you scatter, you make some black hole, and then the black hole starts radiating. And then.
We're going to talk about dynamical black holes, but we're not going to talk about evaporating black holes. Not today, anyway. We can apply operators to the boundary of ADS and send in perturbations which perturb the black hole, which is exactly what we're going to do soon. Okay, so let's talk about precursor operators. A precursor operator, you take, in the case of a quantum circuit, a simple operator will mean one gate. Or one qubit, it could be a 2-qubit operator, that's not important. But let's define a simple operator and call it W. In the Schrodinger picture, it's just W. And let me construct what's called a precursor. The precursor is roughly just a Heisenberg operator with an e to the I h t on this side, t or tau, depending on which kind of time we're using, e to the minus I h tau. That's a precursor operator. We can call it W of tau. I'll assume that W is a unitary operator. It's a unitary operator that you're applying to the system. This unitary operator will have a complexity. I'm interested in how it grows with tau, and then I'm interested in trying to compare it with something in black hole physics. Let's see if we can get a match. Okay. The complexity of this operator at tau equals 0. Tau is equal to 0. It's just the complexity of this single qubit operator. It's 1. 1, incidentally, is a very small complexity. Okay, now, let's think about the quantum circuit version of this. In the quantum circuit version, this unitary e to the I h t is a circuit of length t. Okay? We can think of it, if we like, as a product of gates. G1 dot 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 dot, G dagger 1, G dagger n. I write dagger here because this is the inverse of the time development operator. W, and then symmetrically on the other side, Gn dot 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 G1. This is unitary, W inverse unitary. This is what you would replace it with in a quantum circuit. The quantum circuit architecture for the time being, I'm not specifying in detail, but I'll specify it to be the standard architecture. This is what I would call, for a quantum computer enthusiast, this would be the version of a precursor that I'm interested in. And I'm interested in computing the complexity of this. Now, first of all, I can bound it. I've built it up out of 2n plus 1 gates. So the complexity cannot be bigger. Let's say the complexity of this, let's call it C of tau, cannot be bigger than 2n plus 1. N is this the number of gates? Say it again. Yeah. Okay, let me specify exactly how. With a standard gate architecture, there's k over 2 gates per unit time. So this n is basically time to within a factor of k over 2. Which way does it go? Right. I'll put those things in. But yes, it is related to the time of the circuit. And I'm just being, I'm going to replace this by a standard architecture circuit in a minute. But this is what it's bounded by. On the other hand, complexity is not defined by the number of gates that you use to build the operator. It's defined as the minimum number that you could have. So it could be less than this. This is going to be the first computation which actually makes use of this idea that complexity is the minimum of something rather than the number of gates that you actually used. So we'll see that that plays a role here. Oh. Where's my hooker? I promise to do the same for you when you're my age. Talk about hollow promises.
You have children, right?
I have children, yes. Yeah. But you'll have to rely on my grandchildren because they're all a good deal older than you. But, all right. Let's do this with a standard architecture circuit. And I'm not going to draw both sides of the daggered side and the undaggered side. I'll draw the W and the one side and leave to your imagination the other side. All right, so here is your circuit. I am a great enthusiast for 6 qubit circuits. 1, 2, 3, 4, 5, 6. 4 is not enough to make the point. More than 4 is too hard to draw. And so I strongly advocate 6 qubit circuits in depth 3. All right, so here the left part of the diagram, the daggered part is on the left. Right over here at t equals 0, we'll put in W. All right, so there's W. And then we have a sequence of time steps, each one delta tau equals 1. And in each one of these, let's see, I want to do this right. I put a gate over here, and I'm making the gates with empty holes, empty little circles here. You'll see why empty in a minute. I want to draw this right so that you'll get the picture. All right, there's the first step, the second step. This is arbitrary, of course, but I want to draw a particular case so that we can keep track of stuff. And the last one is over here. I'm sorry, this is taking me longer than I wanted. All right, that's a circuit. And of course, there's another piece on the other side, and I want to evaluate its complexity. The complexity is the minimum number of gates that it would take to make this circuit. Okay, I'm going to show you what's called the epidemic model for computing this circuit. Think of the first qubit, W, as being sick. It has black hand disease, which it got by putting its hand into some black ink. Okay? Now, in the next round here, each person chooses a partner and shakes hands with him. Okay? It's called interacting. What will happen? Well, this person with black hand disease over here, I'll color him in now, white. He will infect the person that he shakes hands with. And so, in the next round over here, there will be 2 sick people. Okay. What about the next round? In the next round, each one of these, each one which is already sick, will infect somebody else. So this one's sick, and he'll infect him. This one's sick, he's already sick, we don't have to infect them, but he'll infect this guy over here. This one over here stays uninfected. Now, in the next round, he's sick. Well, they're both sick, I think. Let's see. Yeah. This one's sick, and so we'll infect him. And this one's sick over here, so everybody is sick. Now, one of the rules about this game is when you're sick, you don't get better. So the circuit just continues with everybody sick. You also don't die, you just stay sick. Okay? You just stay sick, and that's something which is true. Now, the same thing happens on the reflected other side. But I maintain all qubits, all gates which are uninfected, can be canceled against ones on the other side. For example, on the other side here, there's an uninfected gate over here. We can slide this one right through t equals 0 and cancel them without encountering anything that it doesn't commute with. So that means we can cancel a gate over here against a gate over here. Assuming these gates are, of course, G daggers, these gates are G's, they simply cancel. And we can eliminate them. Maybe I shouldn't, I'm going to leave them there for the moment. But we can eliminate them and say the minimal circuit only involves these infected qubits. Now let's define the size of the epidemic at any given time. The size of the epidemic over here is size 1. Size equals 1. Here's size equals 2. Here's size equals 4. Here's size equals 6. And forever and ever and ever, the size is 6 after that. So this is the language that we're going to use. We're going to talk about the size of a circuit. Okay, now we have some more general version of this, the same thing with capital K qubits. And I want to know if at a given time, if the size of the epidemic is S, how many new qubits will be infected in the next step when everybody gets to shake hands again? What is delta S? And this means a delta S for a delta tau of 1. Delta S, this is average. I'll tell you right now what it is. It's S times K minus S over K. Strictly speaking, if you work it out, this will be K minus 1 in the denominator, but that's not important. Here's the way you think about it. We're going to let's lay down one extra gate. What's the probability that that gate involves an infected qubit and an uninfected qubit? Well, the probability that a given qubit is infected is S over K. Number of infected qubits, that's the probability that it is infected. What's the probability that the other one is uninfected? It's K minus S, the remaining uninfected ones, also divided by K. But now each step involves K gates. So I get to multiply this by K. And this is the average number of newly infected qubits, or the average number of newly infected gates. Qubits. Good. Let's turn this into a differential equation. Assume that the number of qubits is large enough to do a differential equation. Same thing, S, K minus S over K. And we can integrate this differential equation. And the answer is S, let's call it of tau, is equal to K e to the tau divided by K plus e to the tau. Let me rewrite that. I'm going to define tau star, it's the scrambling time, but tau star, I'm going to set that equal to log of K. And it is the standard scrambling time for this kind of circuit, log of K, but I'll assume you know that. Then we can write this in the following form, that S is equal to K times e to the tau minus tau star divided by 1 plus e to the tau minus tau star. I will leave this as an exercise for you to go from here to here. You do it by dividing by multiplying by K, and using the fact that tau star is log of K. This is called a logistic function. I don't know why it's called a logistic function, but that's what it's called. And let's just take a look at it. For early times, what do we want to say for early times? For early times, this is small. Imagine tau star is big. This is small, it's negligible, and it's, what am I saying? I want to say that this goes as e to the tau. You can see it easily from here.
Because the K cancels the e to the minus tau.
Yeah, but you can see it very easily from here. For small tau, K over K is 1, and it's just e to the tau, okay? So the size of the epidemic grows as e to the tau, okay? The size of the epidemic becomes, in the quantum theory of black holes and so forth, the size of the growing operator W. The size in the sense I think that Douglas must have talked about. And here we see it growing exponentially. But we see it growing exponentially with tau. Remember, tau is supposed to be, go up on the top there, tau is supposed to be related to, where is it, to the Ringler time, which is 2 pi t over beta. So if expressed in terms, well, we're not doing black holes at this point, we're simply doing circuits, so maybe I should just leave it this way for the minute. But the point is that there's an exponential growth with computer time, and if we wanted to compare that with the growth of operators in SYK or whatever it is, we would replace this tau by t over 2 pi t over beta, which would be the corresponding thing here. So operators grow in this way, but now let's see if we can compute the complexity. I'm going to assume there are no more shortcuts other than just removing these gates which cancel. Okay, how many gates are involved in this circuit? Let's say up to a certain point. Well, we don't need these, those are irrelevant. We have this gate first of all, that's 1, and then we add to it the 2 gates which are here, but we also have to add the 2 on the other side, and then we have to add the 4 gates which are here, plus the 4 gates on the other side, plus the 6 gates here. In other words, to find the complexity, we have to add sizes of up to the end of the circuit. That becomes, we can write that as the complexity when the circuit has reached a certain depth, is 2. The 2 comes from the two sides, the gates on both sides. Integral, or sum, from 0 to tau of the size of tau prime d tau prime. That's just adding up all the gates that didn't cancel. That's the complexity. We can do the integral. Let's do the integral. The integral is k log of 1 plus e to the tau minus tau star. Okay, let's just see how this thing goes. Remember, k is like the entropy of the black hole, although there's no black hole yet. Okay? For small tau, this just grows. For small tau, let's see. For small tau, it's very small. Well, it's small, but it grows exponentially. But what happens for large tau? For large tau, it just becomes log of e to the tau, which log of e to the t minus tau minus tau star. This thing just grows at large time, like k tau minus tau star. In other words, it grows exactly the way complexity is supposed to grow, except that it's delayed. It's delayed by the scrambling time. The growth of complexity is delayed by the scrambling time, and then it starts to grow linearly, the same way it grew linearly up here. Let me draw a little picture to indicate what's going on. What's going on is something like the following. Yeah.
To respect with equation, you don't have to answer.
If what?
It's for respect with you don't have to answer. So this equation for the number of qubits, it looks like a Fermi distribution, but in time.
I think somebody's got to relay the question up. I'm a little hard of hearing. Is there somebody who can follow the question and relay it up to me?
This equation for the number of affected qubits, it looks like a Fermi distribution, but in time.
Like a what kind of distribution?
Like the Fermi distribution.
One person.
It looks like the Fermi distribution. So
Oh,
But in time.
in time.
it does. It does. I didn't even notice that. I don't know what it means. It is called the logistic function. Anybody know why it's called the logistic function? I do not know why.
Population growth.
What's it got to do with logistics? Logistics is what the quartermaster does in the army. I know, I was in the army.
Resources. There's a number of resources, and the population grows until they're eating all the resources, and then it levels off.
And then they eat the quartermaster. Got it. Okay. Yeah.
So where does the tau star appear in the delay in the picture which you just gave? Like it seems that the infection
Okay, yeah, good.
right from the very beginning.
Let's go back to the definition. The definition is W of tau is equal to, let's say, e to the IHT W e to the minus IHT. Okay, W is a small operator in the sense that it only involves a very small number of qubits. Now, let's suppose that W involved no qubits, that it was the unit operator. It's the unit operator on almost all the qubits, so it shouldn't be such a terrible approximation to say it's the unit operator. What happens if it's the unit operator? This completely cancels this, and the complexity is 0 for all times. Or maybe it's 1 for all times, the one coming from this, from the W. Okay, now, on the other hand, we are affecting one qubit, but we haven't affected all the other qubits. It's natural to expect that all the other qubits think that it was perturbed by the unit operator, and they cancel. They cancel until the signal has propagated outward, until what's it called, the Lieb-Robinson kind of signal has propagated out to the other qubits, and then they know that W was not trivial, and they stop being able to be canceled. That's what this picture was doing. So yes, it's closely related to the out-of-time order correlators and that sort of thing, but this is a simple model for it. Okay? And and leads to this kind of exponential growth. Not surprisingly, I mean, epidemics grow exponentially. Okay. Can everybody see this equation over here? K log 1 plus e to the tau minus tau star. This is an important equation. I want to save it, because we're going to compare that with black holes. That's the complexity growth for the epidemic model. Let me just draw what this logistic function looks like. This is the size. If I plot the size exponentially grows, but it starts very, very small. Here is the scrambling time, tau star. It starts out very small and grows, and guess what? If tau star is large, it stays very small up until the vicinity of tau star and then jumps very rapidly. In the limit of large number of qubits, if I rescale the diagram so that tau star stays fixed, it basically approaches a step function. So there's a very sudden thing that happens. The epidemic involves everybody relatively suddenly. Now, what about the complexity? The complexity is the integral under here. It will also look exponential and small, but then when it gets up here, it goes off linearly and continues to grow linearly. This offset tau minus tau star is just basically going back to that point there, which is a short distance away from here on the scale of tau star. And so that's the picture of a precursor in a quantum circuit. Okay. Let's come to precursors in gravity and black holes. Yeah.
But in the case of complexity, it has a maximum that it reaches. So
Yes, it does. It does. This will not go on forever. Will not go on forever. This is during the period when the complexity is much less than maximal. It'll eventually max out at 2 or 4 to the k, depending on whether we're talking about state complexity or unitary in this case. 4 to the k, it will max out. That's right. Yeah.
This is just an average statement, right?
Yes, this is an average statement. Good. Yeah. In my opinion, everything about gravity is an average statement. It's either a thermodynamic statement or a complexity statement.
Does the number of BPS black holes is an average statement?
No. Depends on who counts it. If I count it, yes. You count it, no. Right. Thank God we don't live in a supersymmetric world. But yes, I take your point. There was a BPS paper by Banks, Peskin, and myself, and that I think the answer would be at best average. But no, not good. Okay, here we have our thermal field double black hole, our two-sided eternal black hole. This is t equals 0 over here. But thermal field double at time, I won't even write it. At time t equals 0, we have the thermal field double, and so forth. And at time equals 0, the volume of the wormhole is just 0. Good? No complexity in that sense. Now, what I want to do is apply a precursor. The precursor I'm going to apply is the same kind of thing where you run backward. The first step is to run backward. I may have the wrong. I always get confused of whether I want e to the plus IHT on one side and e to the minus IHT or vice versa. Don't worry, it's okay, I promise. You run backward for a time tau, then you hit the system with a W, and then you run forward. That's basically the same as applying the Heisenberg operator W tau in the remote past. I'm going to take this to be the remote past over here. What does that do to the black hole? We know what it does. It creates a shock wave, a Stanford-Schenker shock wave. So let me put the Stanford-Schenker shock wave in, and I'm going to put it in at time tw in the past. This occurs at time tau or tw, depending on which kind of time we use, and it creates a perturbation which is a shock wave which stays close to the horizon and eventually falls into the singularity. Okay. Now, I haven't drawn the Penrose diagram correctly. For reasons that actually Juan referred to earlier, when you perturb the black hole in this way, it gives a little kick to the boundary, and the boundary goes off in some other direction. But there's a trick. The trick is due to a Tuft and Dre, and the trick is to draw the Penrose diagram the standard way, but use a rule that there's an offset, that the gluing procedure that you needed on the shock wave here involves an offset, what's the right word, a jump from one point to another. And in particular, this is a Tuft-Dre shock wave calculus. A trajectory which actually crosses the shock wave should be displaced along the shock wave by a certain amount that depends on the energy of the shock wave. All right, so you displace it. Did Douglas talk about this? Yeah, okay, good. Then yeah. Right, okay. So now we want to calculate the complexity of this operator, which is now just the complexity at, take t equals 0 over here, t equals 0 over here. It is now the complexity of the new state that's made by applying the precursor over here. And so what we want to do is find the the maximal surface connecting this side and this side. We're going to use maximal surfaces as a stand-in for complexity. So the original surface is no longer a legitimate surface. It has to have a jump in it. The maximal surface would look something like this. That's about what it would look like, roughly speaking. You can calculate it with a jump in here that depends on the energy of the shock wave. The energy of the shock wave depends on when you threw this in. Remote past, a large energy. There's a jump here. And now you can see that there's suddenly, this is dotted, dotted. You suddenly have now volume behind the horizon. So what was originally 0 volume now has a significant volume. You've created volume, and therefore, by this connection, this assumed connection, you've created complexity. Okay, how much complexity, and can I be quantitative about it? With the help of Douglas, it was possible to be quantitative about it. I'm going to give you a master formula. In the presence of a shock wave coming in at time tw, pick 2 points, an arbitrary 2 points at tau left and tau right. They don't have to be at 0. Any 2 points. The following master formula, this is the master formula for the volume of the minimal surface connecting these 2 points. Now, it's not an exact formula, but it is quite close and has the basic relevant features. It was derived by Schenker and Stanford, but for a slightly different purpose. I'm not going to go into it. I will tell you this formula is pretty good. It works, it has all the right features. Okay, so the volume divided by G times LADS. Now this is a pure general relativity calculation, no complexity, is given by log of cosh tau left plus tau right over 2 plus exp, and I'll tell you where these, plus e to the magnitude of tau w is in the past, plus tau star, I think plus tau star, no, minus tau star? Minus tau star. tau star being log k, plus tau left plus tau right, nope, tau left minus tau right, over 2, close bracket. This term here comes from the shock wave. If there was no shock wave, there would only be this. So for example, at time t equals 0, t left and t right equals 0, cosh would be 1, log of 1 is 0, and that would give you 0 complexity at the starting point here. This is the term that's there because of the shock wave, okay? So let's calculate it now. After the shock wave, at tau left and tau right equal to 0, the result will be the complexity of the, should be the complexity of the precursor. We can argue that, but it's sort of obvious, okay? So what do we get? Did I leave something out here? Yes, I did. Yes, I did. Multiplies the entropy of the black hole. Multiplies the entropy of the black hole. Let me just clean it up a little bit. The entropy of the black hole, or if we like, K from the quantum circuit, which we'll identify with a black hole later. I'll write K there. All right, so now we'll set tau left and tau right equal to 0. Complexity at time 0. This will give us logarithm of 1 plus e to the time at which you put the perturbation in minus tau star. And that's all. Tau star is log k. Same log k. Well, come over to here. This is the complexity of a precursor which was applied at time tau in the past. It depends on signs, but this, I think I worked it out so that this was in the past. This is exactly the same formula, except that tau w is now replacing tau, but tau w is the time that goes into the precursor. So it's exactly the same formula. Now, I'm not sure how much we should pay attention to the exactness of the formula. Douglas, should we pay attention to the exactness of this formula? Where's Douglas? No Douglas?
Probably not, I don't know.
Oh, I sure don't. But somehow in this approximation, whatever approximation is being made, the geometry of general relativity knows about the epidemic model. It knows about the epidemic model, which is not totally surprising because the epidemic model is very closely related to the way commutators spread out from out-of-time order correlation functions. This equivalence here, equivalence between an absolutely pure quantum circuit calculation and a pure general relativity, is one of the examples of things that I call GR equals QM, which just means unexpected correspondences between gravity and circuit complexity or other aspects of quantum mechanics. The same correspondence is true for multiple shocks, where you send in multiple shocks and so forth. It all works out in detail. And so this provides a number of not completely independent checks on this idea that complexity and volume seem to go together. Notice that this case here did depend on minimizing the number of gates. We threw away gates that were unneeded. So it wasn't just counting the number of gates that went into defining the precursor, it was the minimal number of gates that could have made the precursor. Okay, let's see, how am I doing? Am I finished? It's 12:30. It's 5 minutes. Okay, so we'll very quickly, good. We can use the same formula to calculate, I'll only do one other example, but I would do some other examples. Question is, what's wrong with white holes? Why do we never see white holes in nature? Well, why do we never see entropy reverse itself? Remember this entropy bounce thing where, why do we never see entropy decreasing? We never see entropy decreasing because the decrease of, among other things, the decrease of entropy is very unstable. If I set up a state which was such that it evolved into the future with decreasing entropy, and I just hit it with a butterfly or less, in a short amount of time, as soon as it took time for the signal to spread out from the butterfly, it would reverse the decrease of entropy, and the entropy would start increasing again. So it takes almost nothing to take a system from decreasing entropy to increasing entropy. The same is true of complexity if this idea of a second law of complexity is correct. If complexity is a kind of entropy of an auxiliary system, the same should be true, but we can also see it gravitationally. Here's the setup. Again, you have your black hole. Now, this is not really a black hole. This is a white hole. This is the region where the complexity is decreasing. It's the white hole. Things can be shot out of white holes. And this is the black hole, or the interior of the black hole. Supposing somebody in the very remote past, a butterfly, perturbed the white hole. How does it perturb it? By sending in a signal, a thermal signal. Let's say a thermal signal. That thermal signal will blue shift as it falls into the black hole and become an intense shock wave. Exactly the situation from before, except now I'm going to say that the shock wave is coming from the very remote past and is therefore very energetic. It will be very energetic by the time we're over here. We have all the time in the past history that the white hole could have been perturbed, or at least all the ways back to some exponentially remote time. So, butterflies in ancient times can perturb it and create these very intense shock waves. Now, let's go up, this is tau W over here. Let's go up to tau, still in the remote past, still in the white hole region, and calculate how the complexity, what happens to the complexity at time tau. In this case, I'm going to fix tau right over here. I'll fix it equal to 0, but it doesn't matter where I fix it. It just comes out as an all-over multiplicative, a additive addition to the complexity, moving it up and down. Don't worry about it. Let's study it as a function of tau left. Okay, so all we're going to do is take the master formula, wherever it is. And here's what we get. Log of 1/2, I'm almost finished, 1, tau left over 2, plus e to the tau minus tau star, plus tau left over 2. I set tau right equal to 0, but if I had not set it equal to 0, there would be an additive term proportional to tau right, but not important. Okay, these terms compete with each other. This one is decreasing. It's what would be there without the shock wave, and it's just representing the fact that you're in a white hole where the complexity is decreasing. This term over here is increasing with tau left, but it's small because tau minus tau star is assumed to be very big. Does that make it small? Oh, it's small in the very remote past. Okay, when tau minus tau. The point is it's increasing. Where is the crossover between these two terms? This one's increasing, this one's decreasing. You can calculate the crossover point, and it's at tau left equals tau W plus tau star. What does that mean? It means you go up a scrambling time, and at that point, the complexity starts to increase instead of decreasing. That's this phenomena that a little flick will shortly after the system has had a time to spread its information around, will start the complexity increasing. Okay? You say, well, that's not surprising. That's the way thermodynamic systems work. That's why we don't see entropy going backward. But remember, nowhere in this are we talking about entropy. We're not talking about the entropy of the black hole. Nothing special happens to the entropy of a black hole when you drop in one thermal quantum. It increases by 1 unit. Nothing special. The complexity radically undergoes a transition from decreasing to increasing, much in the same manner, but it's a complexity phenomena. These are examples. I have others very similar. They always look like thermodynamic kinds of things, but where there's no thermodynamics in sight, only complexity. So my conclusion is that the dynamics of the interior of black holes is governed by complexity in a way which is somewhat similar to the way the dynamics of the exterior, the horizon and so forth, as seen from the outside, is dependent on the thermodynamics of entropy. Okay, that's enough for today, I think.